Carlos, a teacher from Durham School, shares that all through his lifetime, he zeroed in on fostering an exact and clear-cut hypothesis of the universe. He now sees this speculation as something that is scrutinized, something he invites, perceiving that science progresses through such difficulties. The James Webb Space Telescope is reforming and testing quite a large number of long-established ideas in cosmology, uncovering a completely new perspective on the universe. As we enter the new year, the telescope's ultra-deep field picture has shown that there are critical mistakes in our past comprehension of the universe. Initially intended to reveal the main stars of the universe, this telescope is developing into a challenger to past thoughts and may bring about an altogether new way to deal with cosmology. However, not all researchers are terrified of these disclosures. Numerous specialists in the field embraced these changes since it had become increasingly clear that something was amiss with the older hypotheses. The consistency in computing the universe's development rate should feel a little unsure about prior discernments, but for quite a while specialists clutched old presumptions. The astronomical microwave background, CMB, respected as the most seasoned light known to man, started around 380,000 years post-Big Bang, when the universe cooled enough for protons and electrons to bond and make stable hydrogen particles. This period, known as reionization, permitted the universe to become transparent to light. In 1964, American physicists Arno Penzias and Robert Wilson made a forward-leap discovery while working with new radio antenna technology. They identified the CMB. This finding was for quite some time considered one of the most grounded bits of proof for the theory of prehistoric cosmic detonation, procuring Penzias and Wilson a Nobel Prize and getting their place throughout the entire history of stargazing. The CMB offered researchers a novel gander at the early universe, uncovering little temperature changes that made a difference, providing bits of insight into the circumstances that followed the Big Bang. The CMB was additionally used to test the extension pace of the universe and confirm other cosmological presumptions. As soon as the 1920s, space expert Edwin Hubble had laid out that worlds in the far distance were getting away from us with their speed, associating to their distance. This perception prompted what is presently called Hubble's law or the Hubble constant. While Hubble didn't have the high-level observational instruments available today, his revelation, alongside the later finding of the CMB, prompted recalculations of the universe's development rate, which ended up being slower than Hubble's unique gauge. Later, space experts used type Ia supernovae, known as standard candles due to their steady radiance as solid estimation focuses, to measure infinite distances. These recalculations, based on the CMB, proposed a development pace of roughly 67 kilometers per second per megaparsec, while estimations from cosmic explosions demonstrated a higher pace of around 74 kilometers per second per megaparsec. The disparity in these computations has been a place of conflict for researchers for a long time, with numerous analysts understanding that something was essentially amiss with how the CMB and the development pace of the universe were being deciphered. This irregularity, known as the Hubble strain or SAA peculiarity, suggests that there are blemishes in our fundamental comprehension of the universe. These disparities have significant suggestions, testing our most principal convictions about how the universe functions. The problem has been known since the 1990s when researchers began to suspect that there were blunders in the strategies used to gauge the CMB or maybe even in the suppositions made about the universe's extension over the long run. The error between noticed and anticipated development rates became progressively obvious. The Hubble strain proposes that our speculations might require a radical upgrade, demonstrating that key components of our cosmological model could be profoundly imperfect. Now, with the approach of the James Webb Space Telescope, scientists are acquiring phenomenal new information that might be useful to determine the issues with how we might interpret the universe's development rate. These new discoveries are significant to such an extent that they could shake the very underpinning of our past cosmological speculations. The telescope is uncovering cosmic systems and frameworks so antiquated and developed that they suggest the universe's development could have started well before the Big Bang. This challenges the old cosmological perspectives, driving researchers to reevaluate the nature of the Big Bang and the extension of the actual universe. Rather than just discussing mistakes or errors in data, researchers are presently tending to what many describe as an emergency in current cosmological models. It's as of now not simply about errors. It's tied in with re-examining our very origination of the universe. The new information from the James Webb Space Telescope uncovers a universe undeniably more astounding than anything previously envisioned. The Hubble strain, once a source of disarray for those clutching customary hypotheses, is presently a point of convergence for researchers who must stand up to the likelihood that our comprehension of the universe could require to be totally reimagined. As researchers continue to investigate these exceptional disclosures, they are also standing up to the larger inquiry. We really comprehend the universe? To answer this, getting a handle on how science works is significant. Cosmologists utilize complex numerical models, cautious examination of information, and consistent thinking to make expectations and test theories. Their determinations depend on a blend of exact proof, deep-rooted standards, and hypothetical computations. Anyway, recalling that is significant. Science is a dynamic field, and hypotheses are dependably liable to change as new information becomes exposed. The term speculation itself suggests that logical understanding is a continuous course of refinement, not an unadulterated truth. One of the most basic wellsprings of information for cosmologists is the light caught by telescopes, as well as the radiation and sound waves recognized through radio telescopes. All the more as of late, neutrino finders and gravitational wave observatories have added to our comprehension of the universe. The James Webb Space Telescope provides an invaluable tool for considering the earliest cosmic systems, their design, mass, and the quantity of stars they contain. It can likewise follow the development and advancement of cosmic systems over the long run. However, Webb is not without its limitations. For example, it's occasionally hard to recognize far-off universes and huge dark openings that radiate comparable levels of splendor. This acknowledgement drives us to recognize that for a long time, science might have accepted certain suppositions as realities, excusing other conceivable clarifications. The new disclosures from the James Webb Space Telescope highlight the significance of staying open to novel thoughts and speculations. The information assembled by Webb presents a critical opportunity to supplant outdated models with new points of view, similar to how science has, all things considered, developed through weighty disclosures. As researchers continue to unwind the secrets of the universe, they are faced with the challenge of growing new clarifications for what they are finding. These disclosures are causing significant changes in the primary concepts of our comprehension of space, inciting a reassessment of our insight into astronomical development and the forces at work in the universe. Our ongoing models of physics and cosmology are still largely established in the 17th century laws of Isaac Newton. While his laws of movement and gravity have served as the foundation of how we might interpret physical science on Earth, they were eventually found to require change when applied to space. This prompted Albert Einstein's pivotal work in the early 20th century, especially his special theory of relativity in 1905, which changed how we see space, time, and movement. Einstein's general theory of relativity, published in 1915, expanded this progressive reasoning, proposing a numerical model that makes sense of the gravitational impacts of monstrous objects on the shape of spacetime. While Einstein's speculations were crucial in changing our understanding of the universe, he personally recognized their limits. He trusted his hypotheses could never fully represent all the intricacies of the universe and longed for a unified theory that would tie together all of physics. Yet, no researcher has succeeded in accomplishing this extensive model of the universe. It remains an open question: what could this theory look like, and might it ever win someone a Nobel Prize? Among the main suspects for the current cosmological emergency are dark matter and dark energy. These ideas, which make up around 95% of the universe, remain largely hypothetical since neither has been directly observed. While these strange substances are necessary to current models of the universe, their exact nature is still unclear. Some specialists conjecture that they probably won't exist in the ways we expect, requiring alternative clarifications for the noticed development of the universe and the elements of galaxies. Others propose that dark matter and dark energy may have evolved over time, adjusting their properties in ways we don't yet understand. Another possible explanation involves gravity, a force that we know causes attraction between masses. Yet, even this force, which has been described by Einstein's theories of relativity, remains an area of ongoing study. Researchers are investigating the possibility that gravity could have qualities that we don't fully fathom, or that a different, obscure force could be responsible for the gravitational interactions we observe. As the field of cosmology continues to advance, researchers are returning to some of the constants that have long been believed to govern the universe. Cosmology, after all, is a steadily developing field, driven by humanity's endless quest for knowledge. From the early observations of the night sky by ancient civilizations to the modern instruments we use today, each step in our journey to understand the universe has led to new secrets and insights that challenge what we once thought we knew. The James Webb Space Telescope stands as an emblem of our progress in space science, offering exceptional capabilities to explore the universe's origins and the development of galaxies. Launched with remarkable capabilities, Webb represents a leap forward in observational cosmology, enabling us to analyze radiation from the early universe with unrivaled accuracy. Its disclosures have the potential to reshape how we view astronomical origins and development. As researchers continue to concentrate on these discoveries, they face a crucial question. What is our true understanding of the universe? With Webb's data, we now have an opportunity to replace outdated models and expand our knowledge in ways previously unimaginable. The secrets of the universe, from the Big Bang to the questions of dark matter and dark energy, are becoming clearer with each discovery. The fate of cosmology vows to be filled with notable disclosures that will undoubtedly challenge our most established speculations. Science, like the universe itself, is continuously expanding, driven by the quest for knowledge and the marvel of discovery. The James Webb Space Telescope, at the forefront of this ongoing journey, is guiding us toward new horizons, bringing us closer to answering the ultimate questions of existence. How did the universe begin? What is its destiny? And are we alone in this immense universe? These questions are as old as human curiosity, and with each novel observation, the answers become closer and closer to being uncovered.